Let's bend our minds to bending. We've heard quite a bit about bending in this conference, actually. In the first plenary session, Nick talked about the collapse of extruded sections and fracture associated with them, and primarily those fractures are bending failures. And we've had several other talks that have covered issues associated with bending and how important it is. So it's an important characteristic of aluminum alloys, and some of them do very well in bending, and some of them don't do quite as well as we would like from an industrial perspective. In many circumstances, bending, of course, is a cosmetic issue, not unimportant, even though it is cosmetic, such as in hems, on hoods, and those sorts of things, where really any surface cracking or topography issues detract from the appearance of the sheet. But bending, as we saw in Nick's talk, bending failures can also result in loss of structural integrity, and it's important in terms of crash resistance and so on. So it's quite an important property that's sometimes underestimated because you need to assess the performance in bending at quite an early stage in alloy development. There's nothing worse than spending a small fortune of time and money on an alloy development only to find out that at the end of the day, the combination of mechanical properties with bending just doesn't meet the requirements that you have. So it's something that really in alloy development you should look at very early on. There are several different bend tests. I happen to like the cantilever beam bend test, but there are a whole range of them. They give slightly different answers, but in fact, if you compare them, they all scale the same. So whichever test you use, provided you do it correctly, there's no real issue. And bendability is usually expressed in terms of R over T. And I've said in this slide that the bend radius is normalized in terms of sheet thickness. It's not quite right, actually. It doesn't mean that if you measure equal values of R over T for a range of values of R over T for a range of thicknesses, that means that you understand what's happening in the thickness with different thicknesses of sheet. So normalization is not really the right term. But we use R over T because, as you'll see later, it comes up in the equations of strain associated with bending. To understand bending, we need to consider really three issues. I think maybe more, but let's look at three anyway. There's the mechanics of bending. What's going on at a global scale in the bend test? And then there's the plasticity and fracture at the micro level. And then finally, we really would like to be able to predict what the bendability of any particular sheet is in a consistent fashion so that one can compare alloys and materials. The bending mechanics are really straightforward in principle. Essentially, if you bend the sheet, the outer surface, as you all know, is in tension. The inner surface of the bend is in compression. That means that somewhere in the thickness of the sheet, the strain goes from tension to compression, and there's actually a zero strain there, and that's the neutral axis. For low plasticity alloys, the neutral axis is essentially at the midpoint. So if you're looking at really high-strength aluminum alloys, high-strength 7s and 2000s, the neutral axis will sit there round about the midpoint of the sheet. However, in automotive alloys, which is what I'm primarily going to talk about, or transportation alloys, there's a lot of plasticity, and as a result, the neutral axis moves. And from many aspects, which I won't go into, we need to know where that neutral axis is and how it's moving. Now, the basic mechanics of bending were established in the 50s by Sachs and his group, and subsequent to that, there were also various analyses. They're all fairly consistent. the approach to the models that they used was to assume that deformation is in plane strain and in bending of sheet. That's correct. They assume that the maximum strain is tensile on the outer surface, compression on the inner surface, and so we have a neutral axis, and the neutral axis can move or not depending on the alloy, as I said. So that's all pretty straightforward. And for a perfectly plastic sheet, which is what the mechanic models basically assume, the neutral axis radius is given by this top equation. So it's a function of the, as you'd expect, it's a function of the radius of the bend and the thickness of the sheet. For a moving neutral axis, the maximum strain is given by this equation. It's a tad more complicated, but essentially the parameters are the same. It turns out, about 30 years ago when we started looking at this stuff, or 20 years ago, exaggerate, that there were very few experiments that had actually looked at how well these equations performed. How did they deal, how close to experimental results were they? And since we were using these equations for a variety of things, I decided that we should actually check out these equations. We found a paper by Brendan Parker in Australia at Monash about 20 years ago, where he'd used hardness measurements. And he had shown, what hardness measurement showed, that the neutral axis moved, but the technique had too low a resolution to be able to compare with experiments. So we decided to do some experiments that would give us an idea of how these things worked, how these equations work. So experiment, and we've done experiments on a whole variety of hours, but I'm just going to talk about experiments on 1 millimeter sheet of 6111. It's in the T4 temper, and it was water quench sheet. The sheet was then electropolished, and we examined either the through thickness plane or the upper bend surface. And what we did was lay down a grid of carbon contamination spots. And we did it in the SEM by rastering the grid along and basically letting delays at various points. And that gave us a series of a grid of carbon contamination spots. For the basic mechanics equations, we used a grid that was 200 microns in the major strain direction and 25 microns in the through thickness direction. But for looking at the upper bend surface, which I was also interested in, what was going on in terms of the plasticity and damage there, we looked at a grid that was 10 by 10 or even 5 by 10. The sheet bending was done inside the SEM, using an automated 3-point bending rig. And then each contamination spot was electronically given XY coordinates and so on, so that allows us to know where the spots were before and after bending, and so we could back out the strain. Oh. This shows you one of the fiduciary grids that we laid down. This was actually done very early on when we were establishing what the conditions were to get a consistent grid. And you can see we can tag it with column numbers or row numbers, and we can also have the actual XY spots, XY values for those particular, each point. This is the bending rig. And as I said, it's, no, I've destroyed the thing here. If this is the bending rig, it's inside the microscope. This is the bend sample. We can bend it in a controlled fashion, and we used a camera shooting through a port on the SEM rig, and we could measure the bend angle, and we could photograph the the macroscopic bend sample as such, so we could back out the radius of the bends and so on. This shows the strain distribution through the sheet, that's through the thickness of the sheet. So we've got a bend sample, and we're doing that, and we're looking at this plane. And this shows the distribution of strain with distance from the surface for a bend angle of 89 degrees. And you can see that as we move from the surface, which is here, into the sample, the strain drops, as you'd expect from the equations, and at this point, which in this case is somewhere around about 700 microns from the surface, the strain goes to 0, and then into compression if you carry on. This distance, that distance there gives you where the position of the neutral axis is from the surface. These are the upper and lower limits of the strain measurements that were made. These are not multiple samples, it's a single sample. What we're basically doing is concentrating around the apex of the bend and moving either side of that to get the range of strains. And you can see that the scatter is the order of about a strain of about 0.1 when you're close to the surface, and it tends to generally decrease as you go through into the bulk of the sample. This compares the neutral axis motion for a bend of 65 degrees and 142 degrees. This is the 65-degree data. This is the 142-degree data. So you can see that essentially the neutral, and here's the neutral axis at the 0 point, and you can see the neutral axis has moved from that position to that position with the result of the increased bending. So, right, we're okay. The neutral axis is moving, and from comparison of a large amount of different tests and data, the movement is pretty consistent. So that's a comforting thing. So that we can then compare this movement with what the theory tells you, and that's what's done here. This is what the theory tells you, and these are the measurements that we got. So the theory underestimates quite significantly the level of neutral axis motion. And that's pretty well consistent with the 6000 series alloys that we've looked at. 6016, 6010, 6111. They all show this fairly large difference between what the theory is telling you and what the actual degree of bending is telling you. This is not surprising when you look at how the analysis was done. I'm not going to go into that, how the basic mechanics analysis was done, but it's a fairly consistent trend that you get. So if you want to, if you're interested in modeling issues through the thickness of this material, it's rather useful to know where this neutral axis is, depending on the radius of the bend that you make. And it's not a trivial amount of error or difference. The other thing we want to know is what is the maximum strain at the surface of the sample, and how does that compare with theory? And for that, we measured the maximum strain 10 microns below the surface. And this is what that data tells you. Again, the theory is a bit off from the experimental data. The experimental data tends to be above the theory, but the difference is probably pretty minor. I normally don't worry about that difference. So we've been quite comfortable using the theoretical mechanics equation for estimating the surface strains. But you can see that they're actually, it does, the theory does underestimate what the surface strain is. You can see that the, in this particular case, we're looking at surface strain, that's a global microscopic surface strain of about 0.45, that sort of order in this particular case. So what do we get? What conclusions can we make from the bending mechanics then? The motion of the neutral axis is significantly underestimated by the theory, and that's important under certain circumstances. For what we're talking about today and going on, it isn't, but it is important to bear this in mind if you want to compare damage models and so on. And it's important if you're looking at graded structures. In other words, if you're looking at variation in grain size through the thickness, or you're looking at a variation in particle content through the thickness, or you're looking at sandwich panels, it's important to realize, to appreciate where that neutral axis is and where it's going as you're bending it. Because the damage essentially is progressing quite significantly deeper and deeper into the sample. The equation for maximum strain, I think, is in reasonable agreement with the experiments and the variations of data that results that you get. So I think that's okay. Now, what about damage development on the upper bend surface? This is the grid on the upper bend surface, so this outer surface here. And you can see this is only at a bend angle of 36 degrees. It's a very low bend angle. You can see some minor distortions in the grid, as you'd expect, but there are two things that jump out at you. One is, although you can't see it too well in this slide, you will see slip lines in the grains, and you'll also see these features. And these features are displacements at the grain boundaries. Remember now, we've got an upper bend surface. Essentially, the grains of the surface are totally unconstrained, and they displace. And it's not an insignificant displacement. And I'll show you in a minute. If you go to a 90-degree bend, the displacement of the boundaries continue to increase, spread along the length of the boundaries, and you start to see strain localization inside the grains at shear bands, for want of a better word. And we know we are incidentally in plane strain globally. Because locally the situation is different, but globally we are in plane strain. And we know that the susceptibility to plasticity localization is higher in the plane strain condition. This shows the 90-degree, same bend angle, but a rather higher magnification. And here's our grain boundaries with a displacement. And these are intermetallic particles on the surface that at this bend angle have cracked. Now, the interesting thing about this technique is that you can monitor the development of strain around those intermetallic particles as the bending continues and as the damage continues. So it's quite useful. There's a lot of information here, which I'm not going to go into and so on, but it is quite interesting to look at how the local strains evolve around constituent particles, how important they are, the size of the particle is, and also the shape. And experiments like this are really quite interesting, and maybe if you do them, you'll find some things that might surprise you a bit. This is a fib image. Again, this is a 55-degree angle, and oh boy, a pointer has suddenly come back. How do we do that? Okay, this is a displacement at the grain boundaries, and you can see the slip lines going on inside the grains. And some of these displacements are really quite sharp, and if you look at them at higher magnifications and so on, along this displaced surface, you'll actually see evidence of slip lines on that as well. So as this grain is doing that, it's also general plasticity is occurring in the grains. Oh, this is another fib image at a different mag, and here is this grain boundary displacement. And this is really significant displacement. Now, you do see it in tensile samples. And Tony Rollett has done some work on this in tensile samples. We saw it first in significant amount in when we were doing, Mukesh Jain and I were doing hydraulic bulge tests. And we saw these displacements. And it's all a result of the fact that these grains are unconstrained, and the strains involved in bending locally can be really quite high. The number of grain showing displacement with bend angle follows this trend. And you can see that the displacement starts from really pretty low bend angles, then increases very significantly, and then levels off. The number of grains increase, but also the displacement at the boundaries, on the individual boundaries, increase fairly drastically. This is a strain where I've superimposed a strain map over the microstructure underneath. It's 55-degree bend angle again, which is the same as the SEM, the fib shots that I showed you earlier. You can see the boundaries here. Red is the high strain regions, and then it goes down to the blues where the strain is relatively low. Obviously, a deformation, not too surprising, it is incredibly inhomogeneous. And as you continue the bending, the strain, local strains on the boundaries and within some of the grain features, the slip lines inside the grain increase. But the strain also spreads along the boundaries. So the number of boundaries, as you continue bending, the number of boundaries showing the displacement increases, the strain locally associated with the boundaries increases, it spreads significantly along the grain boundary. This is looking at the distribution now at a range of bend angles, and we're covering exactly the same region in the sample. So here's the sample, the measurements we made at a bend angle of 25 degrees, which is very, very low. And then we're going up to 48 degrees, up to 65 degrees, and so on, and eventually up to 95 degrees. Now, this sample is not broken. It's nowhere near broken, in quotation marks, but you can see that the strains are already getting pretty high locally. And in fact, they'll actually get up here on this sort of scale. They'll get up to 0.7 or so, typically. The other thing that strikes you is that localization actually starts fairly early on. Here's an example here where we've got this region where there's a localized strain, and then essentially it grows and grows. It goes up to there, and then when you say it goes up, continue bending, it goes even higher. So localization starts very early on. And this is not differentiating whether I'm at a boundary or anywhere else, really. It's just, and we're looking, as you can see, across a region of about 600 microns either side of the bend apex, which is at the 0 point. So the deformation localizes early and concentrates early. And once you've developed a high local strain area, that will continue to evolve through the subsequent bending process and will carry on. Eventually, the damage will link up, boundaries, intermetallic particle voiding, cracking, and you'll develop these fractures on the surface of the sample, and you're dead. And you can look at the damage process with this technique using the grid carbon spots and grid. You can see how this damage links and how it connects up to give you final failure. So the general comments then, just to recap, the strain is very inhomogeneous, not surprising, localizing, begins at relatively low bend angles, and the surface displacement at grain boundaries also come in at relatively low bend angles. Number of grains showing the boundary displacement increases with bending, and as does the extent of the displacement at any particular boundary. Other damage mechanisms occur at higher bend angles. You'll get localization in significant shear bands. That's a function of the alloy and a bunch of things. Cracking of intermetallics, voiding, and the usual fracture processes that we're all familiar with. And eventually it all links up, and that's that. Okay, so we've now looked at the mechanics, so we now know what sort of strains we are looking at, where those strains are, and we can relate that back to the microstructure of the alloy. We would like to be able to predict bendability. There were a lot of attempts through the 50s and whatever to predict bendability, but Datsu and Yang in 1960 suggested that bendability was controlled by the fracture strain of the material, and once the strain at the bend surface reached that fracture strain, you get cracking, and that would allow you then to develop an equation to predict it. And they used the Sachs equation for in their paper, which if you can get hold of, it looks at a static axis, neutral axis, and a moving neutral axis, and the form of the equation for both is exactly the same. It's of this sort of form, which is really very simple. In fact, if you actually look at the paper, the analysis is a tad more complicated than that, but that empirical equation actually is really very close to the theoretical expression that they developed. So there's this very simple equation. This is the bend radius that you can get where cracking occurs. This is the thickness. This is the fracture strain, and this is a constant. And that constant for a moving neutral axis is in the range 60 to 70, at least in the aluminum alloys that we've looked at. So it's 60 to 70. If you don't have a moving axis, this equation still applies, but C is now down, they suggested 50. The experiments that we've done on high strength 2000 series alloys suggest that it's closer to 40. But anyway, that equation can be used, and we've shown a variety of data plots of this in the literature over the years. Strictly, the fracture strain should be measured in plane strain, of course, because that's our deformation mode. But Embry and the group down there, and also Lewandowski and others, have shown that for aluminum alloys of the types we're looking at, the path dependence of the fracture strain is relatively small when you move from measuring it at the tensile path as against the plane strain path. Remember, we're looking at fracture. We're not looking at the normal FLD minimum behavior that you see at the plane strain position. In fact, the minimum fracture strain is actually at the biaxial position, right? Anyway, there isn't much difference. You can, and we have, measured the fracture strain in plane strain, which is a tedious exercise, but you can do it. And you'll find that the difference is within 3 or 4%. So with the scatter you've got in a normal experiment, I forget about that. This is some data for age material. We've shown a lot of data in the literature, in papers that we published on T4 type materials. This shows that the equation also holds very well for aged material. And this is 6111, and it's been aged over a range of conditions. This is the data, and that's the theoretical line, using 70 as the constant. And we find for 6111, 6016, and alloys around that thing, process as we do it, 70 is what works for us. So that's the value that we use. So the conclusions for bendability are the bendability of aluminum alloys, and it's not just sixes, incidentally. I mean, we haven't found an we haven't looked at an aluminum alloy that hasn't given agreement with that expression. And it's reasonable, right? Essentially, if you achieve a strain at the bend surface that's equivalent to the fracture strain of the material's going to fail. That's the way it is. And we now know from the equations that we showed and the data we showed previously, if you have a profile and you know what the radius of that profile is, and if you know what the fracture strain of the alloy is, you know whether that sheet is going to meet those bending requirements or not. It's really pretty straightforward, really. Now, in addition to that, the fracture strain scales with the yield stress of the material for a constant microstructure relative to the fracture process. And by that I mean it's not the general microstructure, it's what bits of that microstructure are relevant to the fracture process. And if you change the strength while keeping those parameters in the microstructure constant, the fracture strain will scale with that. And that's rather useful, because that means then that you can, in doing alloy development and looking at different alloys, you can, if you know what that scaling is, then you don't have to keep doing bend tests or whatever. You can just interpolate between what the yield stress is doing with a particular treatment or alloy and essentially estimate quite well what the bendability is going to do. This shows that fracture strain yield strength relationship for those aged alloys that I just showed, and you can see the scaling that you've got. So if you have, this is the yield strength, this is the tensile fracture strain, if you have that plot, you can merrily move around quite happily. That data point there, it's not an outlier, it's for very short aging times at 100 degrees C. And it's in a transition point between artificially aged, and this is very likely artificially aged, and naturally aged material. And the scaling line for naturally aged material is different to that for aged material. I'm not going to go into this, whatever, but that's the way it is. So that data point is actually correct, but there'd be another line coming down here that was a natural aging. If we had natural aging data, it would track on a different scaling line. Okay, so we've covered the mechanics of bending, the nature of the plasticity, and how to predict bendability. And I think we can do that all fairly well in a self-consistent fashion. The plasticity associated with grain boundaries is more apparent on a bending surface than it is generally, and the strains locally at grain boundaries can be very, very high. And that's a result of the unconstrained deformation of the surface. It's interesting to think about essentially what does that displacement and strain associated with it tell you about what's happening to the deformation in the grain boundary area within the body of the sample. And you might want to think about that a bit. Plasticity occurs at a range of scales from macro to micro, as you'd expect, and you generate. There's a whole range of topography issues that I haven't even touched here, which is associated on a large scale on the bend surface. You'll see ridges and so on. But they don't appear to significantly affect anything that I've spoken about. They're interesting, and they could have a cosmetic effect in certain circumstances. If you do something stupid like having a huge grain size in the alloy. Bending is controlled by surface fracture, and that's dependent essentially on the fracture strain of the alloy. So if you know what the R over T of the particular profile that you've got you can then back out from that what the strain associated with that surface is. If you know what the fracture strain of the alloy is, and you have plots as we've shown, you can immediately say whether that alloy is going to meet that bending profile or not. Now, there are issues in terms of sometimes, of course, we don't just bend a sample right off the bat. It goes through strain paths and so on, and that's another talk and another issue. But essentially, for an initial assessment of how the alloy is going to do, I think if you use these sorts of approaches, you can estimate very well how the alloy is going to perform in a bending test. The equations are particularly useful in terms of go to the neutral axis issues, movement of that in graded microstructures. Some of the things that Nick was talking about and come up in a couple of other papers at this conference. The neutral axis its motion can have significant influence on the overall bend behavior of the alloy, and it's useful to know what it's actually doing. Anyway, that essentially is as much as I'm going to take of your time. I'd like to thank Mark Gartno and the Serco guys for helping me with some of this stuff, and the numerous students that have toiled through making these strain measurements, which they occur, it looks pretty simple when you see it in a graph, but when you actually go through it, it's a hell of a lot of work. And so we've had, over the years, we've had students from Waterloo, UBC, and McMaster, not all metallurgy students either, who've done a super job generating a huge amount of data and whatever. So thank you for listening. I appreciate it. Just one or two. Okay. Not that I know anymore.
David is willing to answer a few questions if there are any in the audience. Christoph, yes?
Oh. If I'm mobile, maybe, yeah.
No, thank you. That was good, yeah. Oh, Warren, sorry, Warren.
Oh, sorry,
David, thank you for the talk. Have you looked at different quench rates and PFZs and how they affect surface displacement?
We've looked at different quench rates, and as you'd expect, quenching fast is always good. But no, we haven't looked at PFZs and so on. You know, the bend test is really informative in terms of if you have the microstructural tools associated that we now have to look at these bend samples. And we've used the bend test to look at issues of fracture, for example. I think Alexei was talking about fracture and where he has these platelets on the boundaries and so on. And this is an excellent test for this because the grains, you can bend them extensively, the grains expose themselves, and you can then use techniques, well, I wasn't going to go into this, but I think somewhere here. You can then take a bend sample and you can use a fib to erode out a thin foil that's including the bend surface. And that's, what do you do with my pointer, love? Yeah. So that's what we're looking at here. This is the bend surface, grain boundaries here, and here you can see the displacement that you've got associated with it. And those sorts of experiments are really very interesting. This is 6111, and you can, again, there's that bend surface and the displacement that you've got and how that plasticity goes on. These are not trivial strains. I mean, you can get grain boundary strains in 6111 that are 0.9. So these are not trivial strains, but it's a very useful tool to look at things like damage and fracture, basically by using the bend test as a means to look at these features. And then you can do the misorientations across the boundary. What you find is that the boundary misorientation is totally irrelevant to what you see. There are no special boundaries there that are giving rise to this. And Tony rolled essentially on tensor samples much lower strains and lower extents found essentially the same thing. Anyway,
Okay.
I have to sit down now,
Okay, all right.
folks.
That's okay.
I'm sorry.
That's okay. Do you want to sit up here for a bit, or do you want us to have?
No, I can get
Okay,
down
great.
there if
Okay,
you're
Matthew,
helping.
I'm with you.
Thank you.
Matthew.